Alright, so in this video we begin chapter 4, probability. So we are going to discuss basic definitions, and then we are going to discuss the different kinds of events and the different settings in probability given the situation or the given information. So it's going to be, this one is going to be actually one of the biggest chapters, so it might take a while to go over the whole thing. So let's define the basic aspects. So when we talk about probability, so we find probability of events to occur. But what is an event? An event, it's a collection of results or outcomes of a procedure. So that's one of the best definitions we can use for events. Simple event, a simple event is an outcome or an event that cannot be further broken down into simpler components. You will find out later in the chapter how some events can be further described or further broken down into simpler components, like this definition says. Sample space. So the sample space of a procedure consists of all the possible simple events. That is, the sample space consists of all outcomes that cannot be broken down further. So for example, event, rolling a die, simple event, all the possible outcomes. What are the possible outcomes of rolling a die? Well, 1, 2, 3, 4, 5, 6. Well, for a classical die, right? So in this case, the event of rolling a die it's broken down into further or simpler events, which is 1, 2, 3, 4, 5, and 6. Okay, what is the notation that we are going to use throughout this chapter? Big P, uppercase P, stands for probability. And in this case, these are all going to be uppercase letters. The letters A, B, and C. And sometimes, of course, we can go all the way to D, E, F, G, H. And later in the chapter, you will see these examples. These are events. That's how we are going to denote all the different events. P of A, well, in this case, it's not a function like the ones that you are used to in an algebra class or in a pre-calculus class, when you say the function P that depends on a node. This is not what it is. In this case, this denotes the probability that event A occurs. All right. Now, how are we going to find probability? So there are two approaches to determine probability. First of all, let's highlight these keywords or key terms. All right. And well, so the first way to find probability, which we call it the relative frequency approximation. Sometimes we call this the empirical approach. Okay, let me write it down here. Empirical approach. Why is that? Well, so in this case, what we do is conduct or observe a procedure and count the number of times that event A actually occurs based on these actual results. All right. And to calculate that is the number of times A occurred in our observations divided by the number of times the procedure was repeated. Then we have the classical approach to probability, and then in this case we require equally likely outcomes for all the further or the simpler events. And then in this case we assume that the given procedure has n different sample events, and that these simple events have an equal chance of occurring. Okay, if the event A in S of this in n ways, then well, what we do is find the number of ways A occurs and divide that by the different simple events. All right, or the total number of outcomes, if we will. For example, let's go ahead and do the let's describe the rolling a die, for example. Rolling a dice, so for example, if you want to do or to find the probability that we get a 2 on a die, well, how many total possible outcomes do we have in a die? Well, we have 6. So the total is 6. And how many 2s do we see in the dice? Well, that's 1. So the probability will be 1/6. Now, this is using the classical approach. In the relative frequency or the empirical approach, and yes, you might remember the term relative frequency from previous chapters. Right? For example, let's say in this case we do the experiment and we when we roll the dice 60 times, right? That's the number of times the procedure will repeat it. And it turns out that roughly 13 times we got a 60. Well, let's divide and compare these numbers. So if we conduct these two procedures, we may get basically the same. So 1/6 is the same as 0.166 repeats. And 13 divided by 60, that's 0.216. All right. Well, in this case, if we compare the two values, so they're a little bit close to one another, 0.16 to 0.21. Well, I mean, we are expected to get a 0.16 if the die is fair. But in this case, if we do this multiple times, we are going to get most likely a number that is close to that we obtained using the classical approach in probability calculation. Let's see what's next on the next page. So we have more definitions, a few rules in the probability world. Well, the rule number 1, the probability of any event A is a number, could be a fraction or a decimal, so you might want to keep that in mind. Yes, it's either a fraction or a decimal between and including 0 and 1. That is, the probability that the event A occurs goes from 0 inclusive to 1 inclusive. So let's see. That is, in other words, we cannot have no negative probabilities and no probabilities greater than 1. So if you have a probability of 1.1, well, no, that doesn't represent a probability. Yeah, a probability, you can think of probability as a percent as well. So you can have a 0% probability, that's an event that doesn't occur, or you have the probability which is 1 or 100% that is certain that it's going to happen. But you have a 1.23% happen? Well, that doesn't make sense. Or a negative value doesn't make sense either. Probability rule number 2. If an event cannot occur, that is, the event contains no members in the sample space, its probability is 0. And last but not least, probability rule number 3. If an event A is certain, actually I mentioned that when I was describing rule number 1, then the probability of A is 1. So it's, in other words, this is telling us an event that cannot occur, the probability is 0%, and an event that is certain, that you know 100% it is going to happen, well, the probability is 100%. All right. Let's write down sample spaces. So let's find the sample space of rolling a dice. Well, so we already discussed a little bit about it. So sample space, we used uppercase S. And what are the possible outcomes for rolling a dice? Well, if you have a dice, it has a 1, it has a 2, or the dice can land in a 3, or land in a 4, or land in a 5 or 6. right? So that's how we do sample spaces. Well, curly braces and list all simpler events. Find the sample of rolling two dice. So in this case, I typed it to avoid writing too many numbers and waste too much time. So in this case, we are rolling a dice. So notice these are like order pairs. So suppose these two dice, number one, this is a red dice, and the other one is a green. It's a green dice. So if you think of these order pairs as X and Y, well, it's not X and Y. We're not in the algebra class really, but I mean, you can sort of think of those. So X is red, Y is green. So if X equals to 1, that is, the die is red. If it lands on a 1, then the one that has a 1 has 6 more possibilities with the other dice to land in a 1, 2, 3, 4, 5, or 6. If the red dice lands in a 2 first, then there's other 6 possibilities in which the green dice will land in a 1, 2, 3, 4, 5, or 6. And so on and so forth. If the red dice lands in a 3, then you have the green dice to land in 1, 2, 3, 4, 5, or 6, etc., etc. Number 1, we need to specify here total number of outcomes. 6. And then over here, how many outcomes do we have? Total outcomes. We're going to have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 times 6. 36 possible outcomes. All right. So let's describe the sample space of drawing one card from an ordinary deck of cards. So, well, in this case, I just draw the picture, you know. So let's see, in this case, if we were otherwise to describe this in the notation as sample space, so we are going to have an ace. Well, the first row is the clubs, right? Oh, no, is it the clubs? What's the name of? Yes, it's the clubs. A club, 2 club, 3 club, etc., etc. It would take too long to describe this. Then we would have to do all the way till we get the king of club. And then we do the same until we do the ace of, in this case, diamond, the 2 of diamond, so etc., etc., and then until we get the king of diamond. And then that's how we would describe it using this notation. But in this case, I just gave you the picture. You don't have to fill in this blank. That's fine. That's enough. Now, the total number of outcomes, total outcomes, in this case is 52. All right. Okay, let's move on to the next page to see what do we have. Well, so let's draw more sample spaces. So find the sample space for the gender of the children if a family has 3 children. All right, use B for boy and G for girl. Order of children being born actually matters. So let's see how do we describe. So in this case, what we are going to do, the tree diagram approach, right? Tree diagram approach. It's going to be a little bit different. All right. Okay, so what are we going to have in this case? Well, so the couple is going to have the first kid. Number 1. It's going to be a boy. or it's going to be a girl. Boy or girl. So that's the first child. For the second child, it's either boy or a girl. I mean, provided boy goes first, the second possibility, the second kid could be either a boy or a girl. If girl happens first, then the second has the same chance of boy and girl. Let's discuss the third and last. Third and last. If boy, boy, then the third possibility, another boy, another girl. If boy, then girl, then boy, girl. Now, if girl, boy, then boy, and then another girl. If girl, girl, then boy and girl. All right. How many total outcomes? Well, in this case, we are going to describe the sequence of all the possible outcomes. So in this case, over here down below, I'm going to write down S, which is our sample space. And then I'm going to describe every single sequence. Boy, boy, boy. So actually, B, B, B. And then the second sequence, boy, boy, girl. B, B, G. And then this sequence over here to the second branch, boy, girl, boy. And then boy, girl, girl. And then I'm going to go to the other branch, girl, boy, boy. Girl, boy, girl. And then girl, girl, boy. And finally girl, girl, girl. Alright? Now, if we count all the possible outcomes of sequences of babies for the 3 births, we're going to have 1, 2, 3, 4, 5, 6, 7, 8. Alright, so total outcomes. Okay, that's number 8. That's 8 outcomes. So later in this chapter, we are going to discuss a lot of situations in which we are going to develop, these 3 diagrams. All right. So, and these 3 diagrams are very, very important, especially if you are working in, or if your major is dealing with genetics or in biology, in which, every new generation, how it's going to happen. Or if you're in the finance area or in economics when it comes to actually decision making, in the market, in economics again, let me mention it again. Developing this type of diagrams is crucial when it comes to design experiments or so in order to help us make decisions. So you'll see about this, and of course in this case we are going to develop 3 diagrams in which events are dependent or events are independent, in which those events we're going to define soon. Alright, if a family has 3 children, find the probability that 2 of the 3 children are girls. Okay, so how do we find probabilities? Number 1, what is the actual event? Probability that 2 of the 3 children are girls. So let's define event A. 2 girls, right? So that's the event. So the probability of event A, that is the probability that the 2 children are girls, are going to be, well, again, define this, the number number of ways A occurs, divide that by the number of all total outcomes. So I'm going to do the denominator first because, well, that's really straightforward. We got that from the previous step. Well, that's 8 possible outcomes. Now, in how many ways can this event occur? That is, in how many ways can the couple have 2 girls? Okay, let's highlight those. I'm going to highlight all the possible outcomes in which we will see 2 girls. That is, this one right here. All right. This one right here and that one right here. So there's 3 possible ways in which 2 girls can be given to birth. That is, that in which the boy is born first. This one right here. And then 2 girls. All right. Then 2 girls. And then girl, boy, girl. So girl, boy, girl. That's the second sequence. And last but not least, girl, girl, and girl. So those are the 3 possibilities in which there's 2 girls. Oh, wait a minute, girl, girl, boy, not this one. All right, let me fix that real quick. Let me use this to fix it. All right, and this must be still white. All right. Let's see if I can clean this. Yes. All right. Find the probability of getting a red ace when a card is drawn at random from an ordinary deck of cards. So let's define the event A, which is an ace, actually a red ace. All right, so the probability that A occurs, P of A, is the number. Oh, by the way, I didn't finish calculating this. 3/8. We can leave this in fraction or using a graphing calculator. Well, that's going to depend on the homework, what's the format that they want. So the red ace, so again, number of ways that the event A occurs, or number of red aces, that's another way to express it, divide by the total number of outcomes. Okay, so number of red aces. So how many red aces are there in the deck of cards? Well, let's look. So let's look at the aces. They're the first right here, the first column in the picture. And I have 1, 2 red aces. I don't care whether they are hearts or diamonds. They're not being specific actually. Okay, so in this case we have 2 red aces divided by 52 cards. In this case, this is divide that by 52 over 2 is that 26. 1 out of 26. We can reduce. Be careful when reading this type of problem. So in this case, they're asking for a red ace. What if they said the probability that an ace of hearts is drawn? Well, how many aces of hearts are there in the deck? Only 1. All right. Let's move to the next page, see what we have. All right, so find the sample space, flip a coin 2 times. This one is going to be very similar to the couple having the 3 children, except for this is going to be flipping a coin 2 times as opposed to 3 times, as opposed to having three three babies. Okay, so let the sample space, okay, let H be heads and T be tails. Alright, so what's going to happen here? Well, so we're going to flip a coin. Either lands on a head or lands on a tail. Now, if we do the second flip, if the first time happens to land on a head, the second chance could be heads or tails. Otherwise, if it first lands on a tail, then it's equally likely that happens either heads or tails. Of course, assuming that the coin is fair. You know, sometimes there are coins that are kind of tricked in a way that when they are flipped, they always land on heads or they always land on tails. The same happens with the dice. You know, they make them heavy in the part of the die in a way that they land on their heavy side and displaying the number they want to display. Well, of course, this might happen in fraudulent games, you know, or maybe you have seen this in movies when they want to trick one of the players or to make them lose. Alright, so a sample space consists of 154 separate events that are equally likely to occur. What is the probability of each? Well, simply, in this case, the probability, if they are all equally likely, let's say this is A, the probability that A occurs is 1 over 154. Done deal. A class consists of 79 women and 33 men. If a student is randomly selected, what is the probability that the student is a woman? Okay, let the event, so that's the event A. Event A, student is a woman. So the probability of A, again, let me write it in words. That's, how did I wrote it? Give me 1 second. Oh. Number, well, let's say in this case, number of women, actually. Divided by total outcomes, but be careful here. Because the total outcomes are going to be women plus men. Alright? So in this case, how many women do we have? Well, that's 79 divided by 79 plus the number of men, which is 33, giving us a total of 79 divided by 112. And we can leave it like this, indicated as a fraction. We don't have to further simplify this. Alright. In a math class containing 69 students, there are 22 freshmen, 4 sophomores, 3 juniors, and the rest of them are seniors. If a student is randomly selected, what is the probability that the student is a junior, a sophomore, a senior, and a freshman? So we're gonna calculate the probability of each. All right. So event A, let's call this event A. Let's call this event B, and let's call this event C, and let's call this event D. So see how in this case now we're starting to use different letters to denote the different events. Alright, so we can actually do the calculations. However, we need some piece of information. So in this case, math class. This math class has freshmen, has sophomores, juniors, and seniors. The rest are seniors. I'm using SEN for seniors instead of just the S so we don't confuse this with this S. How many are in the class? 69. How many freshmen? 22. How many sophomores? That's 4. How many juniors? That's 3. And seniors, well, let's find out how many seniors are here in this class. Well, not in the one in the problem, of course. 22 plus 4, that's 26. Plus 3, that's 29. And to get the number of seniors, this will be 69 minus 29, which is 40. So there are 40 seniors. All right. Okay. Probability that event A occurs, that is the number of juniors. So the total number of outcomes, I'm not going to do this in words anymore. I'm just going to go, in this case, the total outcomes in the denominator, which is 69. And in the numerator, the number of juniors, in this case, 3. 3 out of 69, which further simplifies to 1 over 23. All right. And then we're going to have the probability of event B to occur. And in this case, well, the probability of choosing a student that is a sophomore. Out of 69, how many sophomores? There's 4. Can we further simplify this one? No, we can just leave it like this. That's fine. P of C. The probability that event C occurs, how many seniors? Well, in this case, total number of outcomes, 69 and 40 seniors. We can leave it like this. We don't have to further simplify this. And last but not least, how many freshmen? The probability that we choose a freshman, that is event D, out of 69. We are going to have how many freshmen? 22. And this one cannot be simplified any further. Just leave it like that. Again, of course, if you want to use your calculator to figure out these results in decimals, of course, go ahead. Let's move on to the next page, see what do we have. Given the probability that a randomly selected student in a class is a female is 56%. Determine the probability that the selected student is male. Well, I mean, the probability that it's male will be the remaining from the female, which is 100 minus 56. That's going to give us a total of 44%. And in this case, notice how we are expressing the probability as a percent. Again, that's going to depend on the situation. So in this case, you may be asked to find probabilities as fractions, as reduced to the lowest terms whenever possible, or decimals, or percentages. So pay attention to the directions when you are being asked to do such calculations. All right, so example 12. A customer's survey asked respondents to indicate their highest level of education. The only 3 choices in the survey are high school, college, and other. If 31% indicated high school and 49% indicated college, determine the percentage of respondents that said other. All right, so what do we have? High school, college, other. That has to add up to 100%. In this case, 31 plus 49 plus other equals 100%. So what do we have? 31 plus 49, that's an 80. 80% are comprised by the people who have a high school and a college degree. And then other will be, well, subtract 80% from 100%. The probability of other, it's 20%. All right. So these are basic, very, very basic calculations of probability. Now we need to define mutually exclusive and not mutually exclusive, and then dependent and independent events. Well, these definitions are going to be very, very important later on when we deal with situations with two or more events occurring at the same time. In some cases, two events may be disjoint or not disjoint. Some kind of union in the event. Well, we will define that soon. Or in the dependent or independent events, that it could be the situation in which the occurrence of one event affects the occurrence of the other one. Okay, so let's see. So two events A and B are considered mutually exclusive or disjoint. That's a new word. Events that cannot happen at the same time. Otherwise, the events are not mutually exclusive or not disjoint. And let me give you an example. So for mutually exclusive, aka disjoint, what do we have? For example, you can think of people having social network. All right. So let's see. The situation for social network. So these are two events that do not have anything in common, by the way. All right. I'm going to do one with one, and I'm going to do one with pink. So social network, like for example Facebook, people who have Facebook in a survey, and the people who have Instagram only. So in this case, none of the surveyed people have both social networks. As opposed to, well, for example, if we put numbers over here, maybe we can think of 35%, and then the remaining, that's 65%. So out of all the 100% of people that were surveyed, 35 have Facebook but do not have Instagram, and 65 have only Instagram but do not have Facebook. So this is a situation in which the events are disjoint or mutually exclusive. In the other situation, not mutually exclusive, not disjoint. In this case, well, what are we going to have? We're going to have a situation. I'm not going to put numbers this time. So there's some people who have Facebook. Oh, there's the people that have Instagram. And then this union right here is the people who have both. All right, so in this case, I'm going to use blue for the people who have Instagram, and pink to denote the people who have both. All right, so those are not mutually exclusive or not disjoint events. All right, so Facebook, Instagram and have both. Is have both, have Facebook, have Instagram. All right. So that's how we do the mutually exclusive and the not mutually exclusive. All right. Independent and dependent events. Well, I like this example right here. So suppose you have a bag of Skittles. So, well, number one, the independent and dependent events. Two events, A and B, are considered independent if the occurrence of A has no effect on the probability of B occurring. Otherwise, the events are dependent. So, Skittles. So, I have a bag with 13 Skittles. All right. So let's see, I have 5 red. And I have 2 yellow. And then 3 blue. And 3 green. Okay, let's make them, I think they have more. So let's keep it this simple. So, well, the probability that we get 1 red will be 5/13. The probability of getting a yellow one, it's 2/13. The probability of getting a blue one, that'll be 3/13. And same for getting a green one, that's 3/13. All right, now that's in the first place for the first event. So let's say 2 events. Define 2 events. A is red and B is it's blue. All right. Now suppose you are going to withdraw 2 Skittles from the bag. Now in this case, we are going to define this whether it is with replacement or without replacement. Okay, so what do we mean by with replacement? So let's say we get the first Skittle, all right, the first Skittle, and if with replacement, if we get whatever the Skittle we get, and then we put it back in the bag, all right. So in this case, this is independent. But otherwise, if we do this without replacement, then we are talking about a dependent event. Because so we want the first one to be red. What is the probability that red occurs? That we get a red Skittle? The probability is 5/3. Okay? So let's say A happens. Okay, so A happens. So the probability of A, with replacement, if we put it back in the bag, then the probability of B event, that is to get a blue Skittle, is 3/13. However, if we don't replace it, if we eat the Skittle, or if we simply don't put it back in the bag, all these probabilities are going to change. So the fact that the first event occurs changes the occurrence of the second event. So if we get a red Skittle, well, on the second withdrawal, this is gonna change to 4/12, and then we are still gonna have our 2 yellow Skittles, but in this case out of 12. We are still gonna have our 3 blue Skittles, but in this case out of 12, and still our 3 green Skittles, but out of 12. Well, we're gonna get more in detail with this type of problems later in the chapter. This is only the beginning of the chapter, and in this case what we're doing is just defining the situation. So we're gonna go back to this later. Another very important piece of information in probability is the complement. The complement of an event A, denoted by A with a bar at the top, consists of the outcomes in which the event A does not occur. So the probability of the complement of A is 1 minus the probability of the event A. Or the probability that the event A occurs is the same as 1 minus the probability that the complement occurs. And well, what we need to keep in mind in this case is that the probability of the event occurs plus the probability that the event does not occur, they add up to 1. Find the complement of each of the following events. So rolling a die and getting a 3. All right. Rolling a die and getting a 3. So the event A is to get a 3. All right. So the probability to get a 3, if you go back to the sample space of rolling a die, 1, 2, 3, 4, 5, 6. Out of the total outcomes, which is 6, in how many ways can we get a 3? Only one, 1/6. So we need to find the complement of getting a 3. In this case, is not getting a 3. In other words, we want the probability that A of the complement, which is 1 minus B of A, which is 1 minus 1/6, and that is 5/6. In other words, not getting a 3 means to get a 1, a 2, a 4, a 5, or a 6. In this case, 1, 2, 3, 4, 5 outcomes. Selecting a letter of the alphabet and getting a consonant. Oh, all right. Okay, so the alphabet contains 26 letters, in which are 5 vowels and 21 consonants. All right. So we want to get the probability of the complement of getting a consonant. That is, so the event A, which is consonant, and the probability is, out of the total possible outcomes, which is 26, we are going to get, we can possibly choose 21 of them. So to find the complement, that's a 1 minus the probability of A, which is 1 minus 21/26. And in this case, 1 minus 21/26 is going to leave us with 5/26. Final answer. Selecting a month and getting a month that begins with an M. All right. How many months in the year begin with an M? Well, we have January, not that one, February, March, April, May, June, July, August, September, October, November, December. Only 2. So, only 2. So, only 2. March and May. That is. So the event A is month begins with M. So the probability that that event occurs, so out of the total number of months in the year, which is 12, only 2 of them begin with an M. So the probability which reduces, well, let's leave it like this. I'm not going to simplify this, so because it's going to make our calculations easier right here when we calculate the probability of the complement. That's 1 minus 2 out of 12, which reduces to 10 out of 12. But in this case, this reduces to 5 over 6. All right. Last but not least, last example. So selecting a day of the week and getting a weekend day. How many weekend days do we have? Well, 2, right? Saturday and Sunday. Thursday and Friday do not count. I know many people say, well, Friday is basically weekend, and many people also say, well, Thursday is the new Friday. Well, no, so those don't count. All right, so A, weekend. Weekend today. The probability of event A that occurs, that's going to be out of the total number of outcomes, which in this case, 7 days of the week, 2 of them are the weekend. The probability that a complement occurs, that's 1 minus 2 out of 7, in this case, 5 out of 7. All right, and this is the end of this first part of the chapter. So we are going to look at the remaining parts of the chapter in the further videos. All right, this is a good place to quit. I'll see you in the next videos.